85% of the universe is made of something you can't see, can't touch, and barely understand, yet it controls the motion of galaxies and the shape of the cosmos. In this video, you're going to explore a single, dangerous idea. What if dark matter isn't just invisible matter, but the foundation of something far more complex than anyone expected? Here is the first hard question. How do you discover something you cannot see, cannot touch, and that does not emit any light at all? You do it by tracking motion. In spiral galaxies like Andromeda, you measure how fast stars orbit at different distances from the center. Close in, speeds of a couple hundred kilometers per second make sense. There is a lot of mass packed into the central region. But when you look way out, 50,000 light years or more from the center, the rotation speed stays around 200 to 250 kilometers per second. It does not drop off the way basic gravity calculations say it should, if only the visible matter is present. With only the stars and gas you can see, those outer stars should not be held in. The galaxy should slowly fly apart at the edges. Instead, the rotation curve is flat. The only clean way to fix this is to add a massive, extended halo of invisible matter around the galaxy. Tens of kiloparsecs across, so the gravitational pull stays strong even far from the bright disk. So the next problem hits you. If individual galaxies already force you to add large halos of dark mass, what happens when you look at entire clusters of galaxies, where hundreds of galaxies orbit a common center of gravity? In these systems, you measure the speeds of individual galaxies, hundreds to over 1,000 kilometers per second, crossing regions a few million light years wide. If you try to hold that cluster together using only the mass in stars and hot gas that you can see, the numbers do not work. The galaxies are moving too fast. The cluster should not stay bound for billions of years. When you add up the gravitational mass that must be there to keep all those galaxies from flying off into deep space, you get a value 5 to 10 times larger than the visible mass. Again, something heavy but invisible fills out the budget. You also see that this invisible matter is spread over huge halos, 100,000 to 300,000 light years across, wrapping each galaxy like a broad three-dimensional shell. Precision lensing measurements reinforce this, because background galaxy images are slightly stretched and sheared as their light passes through these halos. The pattern of distortion matches a lot of mass spread in a big, roughly spherical structure, not just the starry disk. Then comes a sharper question. Could all of this still be a misunderstanding of gravity itself instead of proof for new matter? Maybe gravity behaves differently on large scales, and you have been using the wrong law. To test that, you need a situation where normal matter and any possible dark matter would respond differently. The bullet cluster gives you that test. Two massive galaxy clusters slammed through each other at several thousand kilometers per second. As they collided, the hot gas in each cluster, which is most of the visible normal matter, smashed together, slowed down and heated up so X-ray telescopes see a big bright blob of gas near the collision center. Now you map the total mass using gravitational lensing by seeing how background galaxies are distorted. The surprising result is that the lensing signal peaks not where the gas sits, but out to either side near the clouds of galaxies that pass through each other with little direct collision. In plain terms, the visible gas got stuck in the middle. The invisible mass kept going. That means most of the mass does not collide like gas. It passes through almost unaffected. Modified gravity alone has a hard time explaining why the mass map and the light map separate like this, but a dark matter component that hardly interacts except via gravity naturally does it. So at this point you might think the story is settled. Dark matter is cold, collisionless and boring, just a kind of gravitational background. But here is the twist that reopens the question. Is there any rule that dark matter must be completely inert? Or is that just the simplest assumption you made to get started? The standard model in cosmology, called lambda CDM, treats dark matter as particles that feel gravity and almost nothing else. That assumption works very well on large scales. The distribution of galaxies across hundreds of millions of light years, the pattern of the cosmic web, the statistics of the cosmic microwave background all line up. But when you look at smaller scales, at the detailed interiors of dwarf galaxies and the exact number of satellite galaxies around a Milky Way type system, cracks start to show. One proposed fix is to let dark matter particles scatter off each other with a small but non-zero probability. They still rarely talk to normal matter, but they do talk to each other. Once you allow that, dark matter stops being a completely passive dust and becomes a medium with its own internal physics. That shift leads straight to the deepest question in this whole video. When you talk about life, are you really talking about a special kind of chemistry, or are you talking about a pattern of behavior that could live in any medium with the right rules? In biology, you define life with words like metabolism, replication, and evolution. In physics language, that means you have systems that store information, use energy flows to stay organized, and make copies with variation over time. On Earth, the substrate is atoms, molecules, and visible light. There is no fundamental law that says that has to be the only option. If the dark sector contains more than one particle type, has its own forces, can cool, can form bound states, and can maintain complex structures for the billions of years, then in principle it has the raw ingredients to host systems that meet those physics criteria for life, while never interacting with photons or with ordinary chemistry. In that scenario, most of the universe's biology would be in the dark sector, and everything you can see would just be a thin, bright layer floating inside a much larger, invisible ecosystem. That sounds extreme, so before you lean into it, you need to lock down something more basic. You need to know exactly what dark matter is and is not, as far as current data can tell you, and where the evidence stops and the speculation starts. That is where you go next into the rotation curves, the lensing maps, the relic light from the early universe, and the tight constraints that already tell you dark matter cannot just be more ordinary matter or a simple tweak to gravity. So if you want to know what dark matter really is, where do you start? What is actually solid and what is just guesswork? You start with the places where gravity forces you to admit there is more mass than you can see. First, you go back to the rotation curves of spiral galaxies. Take Andromeda. 50,000 light-years out from the centre, roughly 15 kiloparsecs, you still see stars orbiting at around 200 to 250 kilometers per second, roughly 500,000 miles per hour. If only the visible stars, gas and dust were providing the gravity, those outer stars should slow down. The further out you go, the weaker the pull should get, and the lower the orbital speed should be. Instead, the rotation curve stays almost flat. So what do you do with that? Do you rewrite gravity, or do you add matter you cannot see? The move that works is to surround each visible disk with a massive halo of dark matter, with a density that falls off in just the right way so the gravity stays strong at large radius. Astronomers often call this roughly isothermal, which basically means the density profile gives you a nearly constant orbital speed over a wide range of distances. That shape is not a hunch, it comes from velocity points on a graph, repeated across many galaxies. If you still do not trust the orbital measurements, the next question is direct. Can you weigh dark matter without using how fast things orbit? Can you use light as the probe? That is where gravitational lensing comes in. Mass bends space-time, light follows that curve, so paths of light get deflected near heavy objects. When a massive galaxy cluster sits in front of more distant galaxies, it acts like a lens. You see arcs, stretched images, and small distortions in the background galaxies. You can measure those distortions, often just a few % stretch, across many background galaxies, then run the math backwards to reconstruct where the mass must be in the foreground. When you do that for cluster after cluster, and for large-scale structures, you repeatedly find mass concentrations that do not line up with the visible light. You get mass islands, regions where the lensing signal is strong, but there are few or no bright galaxies or gas clouds. On scales from a few tens of kiloparsecs up to megaparsecs, the inferred mass distribution looks like cold dark matter halos, not like any distribution built only from luminous matter. Now you have two independent lines of evidence saying there is a lot of extra mass. The next step is to ask, Did this dark matter also leave a mark in the early universe long before galaxies formed? That is where the cosmic microwave background comes in. The CMB is microwave radiation at about 2.7 Kelvin, just above absolute zero. Tiny temperature variations across this background have been mapped over the whole sky. Those small hot and cold spots record how matter and radiation were distributed when the universe was about 380,000 years old. Then the universe was a hot plasma of electrons, protons and photons, while dark matter was already there, adding extra gravity but not interacting with light. When you analyse the pattern of temperature fluctuations, you get a series of peaks. Their heights and positions tell you how much total matter there was, how much of that was normal baryonic matter, and how much was dark. The result is sharp. Roughly 26 to 27% of the total energy content of the universe is matter, and only around 5% is normal matter. The rest is dark matter, and its behaviour in those early times fits the idea that it was cold, moving much slower than light. At this point, you cannot just say maybe dark matter is ordinary matter we have not detected yet, because the numbers do not let you. Big Bang nucleosynthesis, the process that produced light elements like helium and deuterium in the first few minutes after the Big Bang, gives you a limit on how many baryons there can be. If you tried to hide all the required dark matter in normal baryons like dim stars, black holes or cold gas, you would overproduce helium and deuterium compared to what you observe. Searches for compact objects also show you cannot pack most of the dark matter into faint stars or small black holes. So maybe you try a different escape, maybe gravity itself changes on large scales, and you never needed new matter at all. Modified gravity theories do exist, and some of them do a decent job of explaining rotation curves for individual galaxies by changing how gravity falls off with distance. But they run into trouble when you look at galaxy clusters, systems like the Bullet cluster, and the full CMB spectrum. It is very hard to tweak gravity in a way that reproduces all those independent observations at once. The combined data pushed you toward a conclusion. The dominant missing mass is non-baryonic, not made of protons and neutrons, and it behaves like a separate component. The standard model of cosmology that encodes this is called lambda CDM. Lambda is the cosmological constant, the dark energy that drives the accelerated expansion of the universe. CDM is cold dark matter. Here, dark matter is treated as particles that move slowly compared to light in the early universe, feel essentially no pressure, and almost never collide or interact except through gravity. In simulations, you model it as a collisionless fluid. Under those rules, you get the large-scale structure we see, the cosmic web of filaments and clusters, and good agreement with CMB data. That success matters, but here is the key tension. If dark matter is exactly what lambda CDM assumes, perfectly cold and collisionless, then it is almost impossible for it to do anything complex. It can clump into halos under gravity, but it cannot cool efficiently. It cannot form bound states with many internal configurations. It cannot support anything you would call chemistry. And if it cannot do those things, then it is very hard to see how it could ever host life. So the real frontier question becomes, how far can you push beyond this minimal, boring picture without breaking the data? Where exactly do rotation curves, lensing, the CMB, and element abundances stop ruling out extra dark forces, dark radiation, or self-interactions that would make the dark sector much more like a hidden world and less like a featureless backdrop? Here is the problem that starts to stress test the boring dark matter picture. When you zoom into small galaxies, the neat clean model begins to slip. In computer simulations of cold, collisionless dark matter, when you let a halo form, the density in the center rises sharply. It forms a cusp. As you go toward the middle, the amount of dark matter per cubic light year shoots up. That is the standard output of these simulations, again and again. Now you look at real dwarf galaxies. These are tiny systems, only a few thousand light years across, a few kiloparsecs at most. You measure how their stars move, you map their rotation curves. If the center is cuspy, the stars close to the middle should feel a very strong gravity spike. and the rotation curve should rise in a particular way, but in many dwarfs you do not see that. The inner regions look more like a core where the density stays roughly flat instead of climbing steeply. The stars move as if the central dark matter distribution has been puffed out and softened, so you have a clear mismatch. Simulations with perfectly cold, perfectly collisionless dark matter like to build cusps. Observations often prefer cores, especially in low-mass galaxies. You can try to blame messy astrophysics, things like supernova explosions blowing gas around and stirring the dark matter, and in some cases that may help, but it does not cleanly fix every system. The question hangs there. Are you missing some important piece of normal physics, or is the basic dark matter model itself a little too simple? Then you run into the next tension, this time not about the shape of a single halo, but about how many halos there are. When you simulate a Milky Way-sized dark matter halo in the standard model, you do not just get one smooth blob, you get a big main halo studded with hundreds or even thousands of smaller subhalos, like a three-dimensional swarm. Many of these subhalos, especially the more massive ones, should be able to hold on to gas, form stars, and show up as bright dwarf galaxies orbiting the main galaxy. But when you actually count the satellite galaxies around the Milky Way and other similar galaxies, you do not see hundreds or thousands, you see a few dozen that are reasonably bright, plus some ultra-faint ones that careful surveys pick up. There is a gap between the raw simulation and the data. This is called the missing satellites problem. You can again try to fix some of it with baryonic physics. Maybe star formation is inefficient, maybe rionization stripped gas from small halos, but then you hit a sharper version, the too big to fail problem. Too big to fail means this. In simulations, the biggest subhalos are so massive and dense that they should not be able to avoid forming stars. They should make clearly visible dwarf galaxies, the kind you would have seen long ago. Those big subhalos, in terms of dark matter, are almost unavoidable outputs of the model, so they are too big to fail at forming galaxies. Yet when you look at the actual bright Milky Way satellites, their internal dynamics do not match those predicted huge subhalos. It is like the simulation gives you a set of heavy, compact, small halos, and the universe says, sorry, those objects are not there. So now you have two kinds of small-scale problems: the inner density shapes in dwarfs, and the number and structure of satellite halos. You can push feedback from stars and gas a long way, but you start to wonder, is there a more direct way to soften and rearrange dark matter on these scales that does not break the large-scale success of the model? That is where self-interacting dark matter comes in, and this is where the idea of the dark sector talking to itself gets serious. The basic move with self-interacting dark matter is simple. You stop treating dark matter as perfectly collisionless, and you give the particles a small chance to bounce off each other. You describe that chance with something called a cross-section, which you can think of as an effective target area per unit mass. Numbers in the ballpark of 0.1 to 1 square centimetre per gram are often discussed. To put that in everyday terms, for each kilogram of dark matter, the target area it represents for another dark matter particle might be roughly like the area of a human hand, instead of being effectively zero. What does that do inside a halo? It lets dark matter particles scatter, transfer momentum, and rearrange energy. In the dense central regions of small galaxies where particle densities are higher, those rare scatterings add up over billions of years. Energy flows from the very center outward, puffing up the cusp into a broader core. The inner density profile gets flatter, which is exactly what many dwarf galaxy observations prefer. At the same time, out in the lower density outer halo, the scattering is so rare that the large-scale structure and lensing maps look almost unchanged. So you keep the big successes of cold dark matter while tweaking the small scales. You then ask, is there any hint in galaxy clusters that dark matter sometimes scatters with itself, beyond the bullet cluster story where it looked mostly collisionless? In some cluster collisions, when you compare the hot gas, the galaxies, and the lensing maps, you see possible small offsets or extra spreading in the inferred dark matter distribution. These are not clean slam dunk cases. The data are noisy, the modelling is hard, and different groups argue about the details. But the key point is, These observations do not rule out self-interactions at the levels I just mentioned, and in some setups they may even mildly prefer them. That keeps the idea alive that dark matter does not just follow gravity silently, it might be bumping into itself very occasionally in ways that change halo structure. Once you accept even a little bit of self-interaction, a bigger door opens in your mind. If dark matter particles can scatter, why stop there? Why not consider that they might also feel forces in a hidden sector, have bound states, or radiate some kind of dark energy? You do not have to add all that at once, but you see the path. First you go from no interactions at all to rare elastic scatterings. Then you ask whether the same hidden physics could also allow dark matter to cool, to collapse more efficiently along certain directions, to form disks, clumps, filaments, and clouds that are much more structured than a simple smooth halo. And here is where the tension in this video starts to climb again. Because whenever you have a medium that can cool, clump, and form long-lived structures on many scales, you start to get the raw material for self-organization. You get regions with different densities and temperatures, you get flows of energy, you get the possibility of stable information storing configurations inside the dark sector. On its own, that does not mean life, but it is getting closer to the kind of environment where life, in a physics sense, becomes thinkable. The big question that follows, and that you have to face next, is this: if dark matter can bump into itself, can it also feel its own version of electromagnetism? Can there be dark forces and dark photons building a hidden kind of chemistry? Here is the next uncomfortable question. Why do you assume the dark sector only gets gravity when your O matter gets a full toolbox of forces? In the standard model, every interaction you know comes from fields and particles that carry those fields. Photons carry electromagnetism, gluons carry the strong force, W and Z bosons carry the weak force. Those are gauge bosons, and they come from underlying symmetries. So if there is a whole dark sector making up most of the matter in the universe, there is no good reason, from pure theory, that it should be stuck with just one weak, slow force like gravity. It could have its own gauge forces, with its own carrier particles, including something that behaves like a photon, but only couples to dark matter. That is what people call a dark photon. In that picture, some dark matter particles carry dark charge, they feel attraction and repulsion in a way that mirrors electromagnetism, but they do it in a channel that completely ignores ordinary light. If that sounds too speculative, the next step is to ask a hard, practical question. Can you test the existence of dark photons in a lab on Earth? Or is this forever stuck in theory? There is a small loophole in the idea that lets you get a handle on it. Even if dark photons mostly live in the dark sector, they could mix very weakly with ordinary photons. Think of it like a tiny probability that a dark photon and a normal photon swap identities. This is called kinetic mixing. If that mixing is not exactly zero, then dark photons can produce tiny, unusual signals in experiments built to stare at photons and electrons with high precision. So physicists build beam dump experiments where they slam high-energy electrons or protons into a target and look downstream for weird particles that survive the dump. They run collider experiments and high-precision atomic measurements that are sensitive to extra, faint interactions. These setups can, in principle, spot a dark photon in a mass range from well below 1 electron volt up to billions of electron volts, if it mixes strongly enough. So far, nothing has clearly appeared, which means the mixing must be very small. But small is not the same as zero. There is still a wide range of masses and couplings that experiments have not closed off. That keeps the door open for a dark photon that is almost completely hidden, but still powerful inside the dark sector itself. Now the really important question, if such a dark photon and dark charges exist, what does that do to dark matter on large scales? The answer is big, because once you give dark matter more than one charge species, with opposite charges under this dark electromagnetism, it can form bound states, the dark equivalent of atoms. You can have a heavy dark proton and a light dark electron orbiting each other, held together by the dark photon. That pair is a dark atom. If the dark sector has more than two types, With different masses and charges, it can build more complex bound states. A gas of these particles at high temperature would form a dark plasma with free dark charges and dark photons bouncing around. As it cools, dark charges recombine into dark atoms, and those atoms can emit dark photons when they change internal energy levels. That is exactly how ordinary gas cools, by emitting visible or ultraviolet light. The only difference here is the radiation never shows up in your telescopes because it is dark light, coupling only to dark charges. With this mechanism, dark matter is no longer locked in a hot pressureless halo. It has a way to radiate energy away and settle down. That leads directly to the next tension. If dark matter can cool by emitting dark photons, how much structure can it build, and on what scales? In the standard cold dark matter picture with no cooling, halos form by gravity. They virialize, they keep random motions, and they stay puffy with sizes from kiloparsecs to megaparsecs. They do not collapse into thin disks on their own. But if a fraction of dark matter can emit dark photons, it can lose kinetic energy, sink deeper into potential wells, and contract. A large halo that starts out hundreds of thousands of light years across can, over billions of years, develop much smaller, denser components. You might then get dark clouds only a few parsecs across, a few light years, spread through the halo the way molecular clouds are spread through the Milky Way's visible disk. Those clouds would have higher densities, shorter internal timescales, and stronger energy flows. They could collide, merge, fragment, and create a whole range of structures from subparsec scales up to galactic scales. This is exactly the sort of rich multi-scale structure you rely on in normal matter to get stars, planets, and eventually biology. You go from one big, smooth component to a layered, clumpy medium with many environments and many physical conditions. So the next thing you have to ask, and this is where the idea of dark life stops sounding like pure fantasy and starts sounding like a constrained possibility, is whether this dark chemistry can support complex information processing. You're not talking about carbon, oxygen, and nitrogen here. You're talking about whatever particle zoo the dark sector gives you. The key requirement is that you have more than one particle type, more than one kind of bound state, and a spectrum of energy levels and interaction strengths. With that, you can build reaction networks, where different dark atoms and dark molecules collide, stick, break apart, and rearrange. Those networks define a chemical space, a landscape of possible compounds and reactions. In that space, you can ask very direct questions. Are there long-chain structures, the dark equivalent of polymers, that can store information in their arrangement? Are there reaction pathways that can copy those structures with small errors, providing variation? Are there environmental energy sources, like dark radiation fields or gravitational potential differences, that can drive cycles far from equilibrium? If the answer to those questions is yes, even in a narrow corner of parameter space, then the dark sector becomes a plausible platform for life in the physics sense. You have matter that can remember its own patterns, compute updates to those patterns, and build copies of them, all inside a medium that normal telescopes will never see. The disturbing part is that none of this automatically contradicts what you already measure. A mostly collisionless, cold component can still dominate the mass, matching large-scale structure and the cosmic microwave background, while a smaller dissipative dark component does its own thing, forming dark atoms, dark disks, and dark chemistry. So the pressure point now is clear. Where exactly are the observational limits that say this much hidden dark physics is allowed and no more? And within that allowed region, how far does the possibility of dark life really extend? Here is the hard question you have to face now when you say life. Are you really talking about specific chemistry, or are you talking about a kind of a physics pattern that could live in any medium that can store and process information? Biologists use words like metabolism, homeostasis. Those are useful, but underneath they all describe one thing: structures that stay around for a long time, stay out of thermal equilibrium, and manage energy and information well enough to keep going. On Earth, that structure is a cell with DNA or RNA inside, using chemical energy to maintain order. But if you strip away the details, what you really have is a physical system that takes in low entropy energy, does work, dumps waste heat, and uses information to stay organized longer than it should. So you can rephrase life in pure physics terms as long-lived, out of equilibrium structures that process information about their environment and themselves. They have internal states that matter, they update those states based on incoming signals, and they feed on energy gradients to keep running. That is not tied to carbon or water or a 20°C room. In principle, any substrate that can store bits and has rules for flipping those bits in a controlled way and has an energy source can implement something that fits those criteria. When you look at it that way, the question shifts from could dark matter have cells and DNA, which is too narrow, to could the dark sector support information processing structures that meet this physics level definition of life? Once you frame it like that, the next step is obvious. Can dark matter even act as a computational medium, or is it too simple? In the most boring model, dark matter particles barely interact at all, so there is not much you can do with them. But if you allow self-interactions, bound states, dark atoms, dark molecules, you suddenly have a lot more structure. Different internal states of a dark atom can play the role of bits, like 0 and 1. Different configurations of dark molecules can store more complex information, like words and sentences made out of an alphabet. Then you add rules, which adjust the dark sector's version of chemistry. When molecule A hits molecule B with a certain energy, they combine into C. When C absorbs a dark photon of the specific energy, it splits back into A and B. Those are logical operations, cause and effect rules that map one set of states to another. The energy needed and released in each step is carried by dark radiation, dark photons. If you put all of this inside a dark cloud a few light years across, with a decent dark matter density, the number of possible bits you could pack in there is huge, far beyond all the transistors on every chip on Earth. Even if only a tiny fraction of that capacity is actually used, the headroom for complexity is enormous. But capacity alone is not enough. You have to ask, does the dark sector have the time and energy to actually run these computations? Dark halos around galaxies have been in place for more than 10 billion years, which is around 10 to the power of 17 seconds. Human technological history is maybe 10,000 years, which is tiny compared to that. Even if the basic interactions in the dark sector are slow, maybe one useful reaction per year in a given local region, over 10 billion years you still get 10 billion steps. Multiply that by the enormous number of possible locations in a halo, and the number of total clock cycles available to dark matter is absurd. Where does the energy come from to drive all this if dark matter does not use starlight? You have several possible sources. As dark gas collapses under gravity, it heats up and can radiate dark photons, creating flows of dark radiation. Accretion onto denser dark objects can produce shocks and turbulence. If there are dark stars powered by annihilation or dark sector reactions, they will emit steady dark light for millions or billions of years, the same way normal stars power planetary climates. All of these are gradients, differences in energy density that can be harvested by any system able to absorb and use dark photons. In other words, the dark sector has both the runtime and the energy budget to support very long, slow, but extremely large-scale computation. Now you might push back and say, complexity without visible light sounds strange, but your own planet already shows you that light is just one option. Deep in Earth's oceans, far from the sun, there are ecosystems around hydrothermal vents. They run on chemical energy from the planet's interior, not on sunlight. The organisms there are blind to photons from the sun. They live off temperature gradients and chemical reactions. They have DNA, metabolism and evolution, but their energy input is basically hot fluid mixing with cold water. So the lesson is simple. You do not need visible light, or any light, to get complex adaptive systems. You only need gradients, feedback and a medium that can store and update information. Generalize that to the dark sector. Dark life would not care about photons at all. it would be completely invisible to your telescopes by design. It would evolve and expand inside dark clouds, dark disks, and dark halos, reacting only to dark forces and gravity. It would see your stars only as small perturbations in the gravitational field, the way you see supermassive black holes only through their influence. From the dark sector's perspective, your whole luminous universe is just a thin, noisy layer sitting inside its much larger environment. This leads to a brutal observational limit. If such dark biospheres exist, how would you ever notice? They give you no normal light, no radio signals, no infrared heat you can pick up. The only channel that connects you is gravity. So you are limited to asking very indirect questions. Do dark matter distributions in galaxies and clusters look the output of simple passive physics? Or do they show signs of being sculpted by some process that seems to optimize, organize, or redistribute mass in non-trivial ways? You look at halo shapes, substructure statistics, time evolution, and compare them to simulations with different dark physics. That is a hard test, because gravity alone can already produce quite complex patterns. But if dark life is real and widespread, over billions of years it could leave subtle but systematic fingerprints. For example, certain mass ranges being depleted, certain types of subhalos being rarer than simple models predict, or particular disk-like components showing up where there should only be puffy halos. The challenge and the tension is that you're trying to decide whether the universe is shaped only by simple rules plus chance, or whether there is an extra layer of organized behavior hiding in the dark mass. So you arrive at a sharp next step. If gravity is your only messenger, you need to look for dark sector engineering in the only place you can, in the detailed structure of halos, disks, and subhalos around real galaxies. That means asking, could some of the odd features you already see, like possible dark disks or missing substructure, actually be the side effects of dark matter that is not just interacting but actively organizing itself? So if dark matter can interact with itself and maybe even cool, what does that actually do to the shape of a galaxy? Does it stay as one big fuzzy halo? Or does it start building new structures of its own right on top of the ones you already see? That is the key jump from boring background to second hidden architecture. Start with the basic difference, collisionless versus dissipative. In the standard cold collisionless case, dark matter falls into halos under gravity, mixes around and settles into a stable profile where the density is highest in the center and falls off with radius. In simulations, you often get something close to what is called an NFW profile, dense inner region, then density dropping roughly like 1 over radius squared out in the main part of the halo. There is no efficient way for this dark matter to lose energy, so it stays in a puffed up, roughly spherical configuration, a few 100,000 light-years across, tens of kiloparsecs. Dissipative dark matter models change one thing. They let dark matter radiate away energy in the form of dark photons or some other dark radiation. Once you let that happen, dark matter does not have to stay puffy. It can cool, contract, spin up and flatten into a disk, just like ordinary gas does when it cools inside a halo. In that case, instead of having only one big halo, you can have a big halo plus a thin, rotationally supported dark disk embedded inside it. Gravity is still in charge overall, but the cooling lets the dark component reorganize itself into tighter, more ordered structures. So then you have to ask the obvious, could your own galaxy, the Milky Way, already be hiding a dark disk that you have only seen indirectly? The visible disk of the Milky Way is about 30 kiloparsecs across, roughly 100,000 light-years, and a few hundred parsecs thick, around 1,000 light-years. It is a thin, rotating structure of stars and gas sitting inside a much larger dark halo. A dark disk, if it exists, might have a similar radius, but be thinner and possibly more massive than the visible disk. You cannot see such a dark disk directly, but you can feel it through the motions of stars. Stars near the Sun oscillate up and down through the galactic plane. Their vertical motions, a few to tens of kilometers per second, over distances of a few hundred parsecs, tell you how much mass is packed into the disk region. If there were a very massive razor-thin dark disk right in the plane, the vertical gravity would be stronger, and the oscillation patterns would shift. Surveys that measure stellar velocities and positions try to fit models with just visible matter and a standard halo, and then ask how much extra thin mass they can sneak in before they ruin the fit. The current results do not demand a dark disk, but they do not completely rule out a modest one either. Some analyses allow a double disk setup, one disk made of stars and gas, one denser and thinner layer made of dissipative dark matter, with a total surface density maybe comparable to or somewhat below the visible one in the solar neighbourhood. If that is true, then right now, as you orbit the galaxy, you could be passing through a region where a second invisible disk of matter is also spinning, sitting almost on top of the one traced by stars. But if there is a dark disk, is it smooth? Or does it have its own clouds and clumps the way the visible disk has molecular clouds and star-forming regions? Once you give dark matter enough internal physics to cool efficiently, it is natural for it to fragment. Ordinary gas in a disk breaks up into clouds a few parsecs across, a few light years, with higher densities and lower temperatures than the background. Gravity pulls them together, pressure pushes back, turbulence stirs them. Over time, those clouds can collapse further and form stars and planetary systems. A dissipative dark disk could go through the same hierarchy. Large-scale flows feed smaller-scale overdensities, which then cool and collapse into dark clouds, maybe 1 to 10 parsecs in size. Inside those clouds, the density of dark matter would be much higher than in the surrounding disk. The interaction rate would be higher, and the conditions would be more stable over long times. Instead of forming bright stars that you can see, these regions might assemble long-lived dark structures stabilized by dark forces, or complex networks of dark-bound states. From your point of view, those would just be slightly denser patches in the dark mass, but from the dark sector's point of view, they could be the key neighborhoods where complex behavior is sustainable. So how do you even start to test whether a dark disk and dark clouds are there, if you never see them directly? You go back to gravity again, and you look for small systematic deviations in how stars move. A thin, massive dark disk would change the precession of stellar orbits. How the direction of the orbit slowly rotates over time, it would change the amplitude and period of stars' vertical oscillations, how far above and below the plane they travel. It would slightly tweak the local gravitational potential, which you can infer by measuring millions of star positions and velocities with high precision in kilometers per second over kiloparsec scales. You then compare those measurements with models that include only the visible disk and a standard halo, and with models that also include an extra thin disk of hidden mass. If the data prefer a razor-thin mass component, something that looks like an invisible slab in the galactic plane, that is strong evidence that the dark sector is not just a smooth halo, but has undergone dissipation and organization. You're essentially using the Milky Way as a detector, reading off ghost structures from tiny differences in stellar motion. This brings you to a larger scale question. If a piece of dark matter can cool into disks inside big halos, could there be entire galaxies that are mostly or even completely dark with their own internal dark disks and dark clouds, but almost no stars? You already know about almost dark systems. Ultra-diffuse galaxies can have sizes similar to the Milky Way, tens of kiloparsecs across, but with very few stars spread thinly so they look like faint smudges. Some gas-rich dwarfs, like a GC 198691 and others, are heavily dark-dominated, with much more mass in dark matter than in baryons. They sit close to the edge of what you can detect. Push that idea one step further, and you get fully dark galaxies, halos that never formed many stars at all, or lost them quickly, but that still contain a dissipative dark component. Those objects would be basically invisible in ordinary surveys, no starlight, maybe very little gas emission. You would only find them through their gravitational effects, for example as lenses that distort background galaxies, or as unseen perturbers that tug on stellar streams and satellite galaxies. In a dissipative scenario, such dark galaxies would not be empty. They might host their own dark disks, dark clouds and internal structure, completely untouched by starlight. From their perspective, your bright baryonic galaxies would be irrelevant. And if the dark sector is capable of complex chemistry and information processing, those dark galaxies would be potential habitats, large-scale environments where dark ecosystems could grow for billions of years without ever intersecting with normal matter except through gravity. That pushes the tension up another notch, because now you're not only asking whether the Milky Way has a hidden dark disk, you're asking whether the universe is filled with entire dark systems that you barely see, and whether some of the missing or weird structures in your maps are actually those hidden objects. The next step, once you accept that possibility, is to ask whether the dark sector can go even further, building star-like and planet-like structures of its own, with stable energy sources and long-lived orbits. The basic architecture you know is friendly to life. How far can dark structure go? If you already allow dark disks and dark clouds, do you have to stop there? Or can the dark sector build its own versions of stars and planets as well? That is the next step you have to take seriously, because once you have dense regions of dark matter, with self-interactions and maybe annihilation, or other exothermic reactions, you automatically create places where a lot of energy is released in a small volume. In many dark matter models, when two dark particles meet, there is a chance they annihilate into lighter dark particles, or into dark photons. That means the power output in a region scales very sharply with density. Pack more dark matter into a small space and the rate of energy release rises fast. In the early universe, before normal stars formed, some scenarios say there were objects hundreds to thousands of times the mass of the Sun, where ordinary gas collapsed into a dark matter-rich core. There, the annihilation of dark matter supplied enough power to puff up the object and keep it stable. These are called dark stars, not because they are dim, but because their light would be in dark photons, completely invisible to you. They would sit at the centers of dense regions, shining in a spectrum you cannot detect, while pumping out a huge amount of dark radiation. The next thing you have to check is stability and lifetime. Are these dark stars just brief flashes, or can they last long enough to matter for complex systems? For normal stars, the rule is simple. The lifetime depends on how much fuel you have and how fast you burn it. High-mass stars burn bright and die fast, a few million years. Low-mass stars sip their fuel and can last tens of billions of years. Dark stars, if they exist, would follow some version of the same logic. Their fuel could be the local dark matter density, plus whatever mechanism feeds new dark matter into their cores. If the annihilation or reaction rate is very fast, a dark star might only live for a short window in the early universe, millions of years. But if the process is slower and the dark matter supply is maintained, you could get lifetimes reaching billions of years, similar to or longer than the Sun's. That matters because complex structures do not appear overnight. They need stable energy sources that last many, many orbits, many thermal cycles, a huge number of microscopic reactions. A population of long-lived dark stars would provide that steady background, like dark power plants scattered through a halo. Once you have dark stars, the next question is not optional. Do they have things orbiting them? Gravity does not care whether the mass is baryonic or dark, it works the same way. Any clump of mass will attract others, and if some of those others have angular momentum, they end up in orbits. So around a dark star, you should expect some kind of bound structures. Call them dark planets, dark moons, or dark rings, depending on the configuration. Their orbital periods could range from hours to days to years, depending on the star's mass and the orbital radius, just like in normal planetary systems. The key ingredients are cooling and stability. If the dark sector can radiate away heat via dark photons, then smaller clumps of dark matter can contract into compact bodies, the analogues of planets, instead of staying as diffuse clouds. Once formed, those bodies can settle into nearly circular orbits. The gravity sets up gradients in potential energy, and the dark radiation sets up gradients in temperature. That creates different environments at different distances from the dark star, with different energy fluxes and interaction rates, exactly the kind of variation you need to support diverse structures and processes. This leads directly into the idea of a dark habitable zone. In normal astrophysics, the habitable zone around a star is where liquid water can exist on a rocky planet's surface, not too hot, not too cold, That is just one specific way to say the conditions are right for long-lived complex chemistry. In the dark sector, replace liquid water with whatever phase and reactions are relevant for dark chemistry. You define a zone where the flux of dark photons, the typical bond energies of dark molecules, and the density of dark matter all line up so structures do not instantly freeze into a rigid solid or evaporate into a random noise. That zone could easily span tens of astronomical units, tens of times the Earth-Sun distance, around a given dark star depending on its luminosity and dark photons and on the dark chemistry involved. Within that region, dark bodies and dark clouds could host biospheres, in the physics sense, volumes where information-storing structures can persist and evolve. You do not need Earth-like temperatures, you just need a regime where reaction rates and error rates in copying are in a sweet spot, not zero, not overwhelming. Now you reach the observational choke point again. If these dark stars and dark planets exist, how could you ever pick them out when they do not emit or reflect normal light? The only channel you still have is gravity. A collection of dark stars orbiting in a galaxy adds to the galaxy's mass, and that mass curves space-time. You can, in principle, see their presence through small anomalies in stellar motions or through micro-lensing events, where a compact mass passes in front of a background star and briefly magnifies its light. Surveys that will look for compact dark objects, from Earth mass up to star mass, already do this kind of search. Microlensing campaigns have tracked millions of stars, looking for short-term brightening that signals an unseen mass moving across the line of sight. The statistics of those events put limits on how much of the dark matter can be in the form of compact objects, such as black holes or dense clumps, over different mass ranges. These constraints are real. They rule out a universe where almost all dark matter is in solar mass black holes, for example, or in asteroid mass nuggets. But those limits are not absolute zero. There is still room for a fraction of the dark matter, maybe a few percent or less, to be in the form of compact dark star, like objects spread through halos. There is room for swarms of lower mass bodies below current detection thresholds, especially if they sit in regions that have not been monitored well. There is also room for dark stellar systems that are not purely compact. For example, a dark star surrounded by a lighter, extended dark atmosphere, which would lens more weakly and be harder to categorize. The tension is this: you already know that some compact dark structures are excluded by current data, but you also know that a mixed dark sector, with a dominant smooth component plus a smaller population of dark stars and dark planets, is not fully ruled out. That leaves open the disturbing possibility that there are dark stellar systems threaded through your galaxy right now, cutting across stellar streams, sitting in the same halos as visible stars, and you have only scratched the surface of what their gravitational fingerprints look like. So the next logical move, if you want to test any of this, is to use the most sensitive gravitational probes you have, the thin cold structures in the visible sector that react strongly to small perturbations. That means stellar streams, satellite galaxies, and other fragile tracers. The question you have to push on is simple and sharp. When you read the fine structure in those tracers, are you seeing only the clumps from standard dark matter and normal subhalos? Or are you also seeing hints of extra, organized dark systems punching gaps and warps into the visible galaxy? How do you actually look for something that might be alive in the dark sector, when the only thing it does to you is pull on your stars? You use the most sensitive test masses you have, and in the Milky Way, that means stellar streams. When a globular cluster or a small dwarf galaxy orbits the Milky Way, tidal forces slowly tear it apart. The stars get stripped out and stretch into a long, thin stream, tens of kiloparsecs long, so tens of thousands of light years. Dynamically, those streams are like seismographs laid across the dark halo. If a dark matter clump with a mass of 1 million to 100 million suns, 10 to the power of 6 to 10 to the power of 8 solar masses, flies through at a few hundred kilometers per second, it kicks the stars and carves a gap or a kink in the stream. So the first key point is simple. Every time a dark subhalo crosses a stream, it leaves a gravitational bruise. Those bruises do not heal. They stay as underdensity, slight bends, wiggles in the positions and velocities of the stars. Over billions of years, a long stream accumulates multiple hits, so the pattern of gaps along it encodes how many dark clumps there are, how massive they are, and how they are distributed. If dark matter is just a smooth fluid with no small clumps, the stream stays almost perfectly thin. If it is full of subhalos, the stream looks scarred. The next question is, can you actually measure those scars cleanly enough to learn anything, or is this just nice theory? With current surveys like Gaia, you can. Gaia measures positions of stars to microarcsecond or milliarcsecond precision, depending on brightness. At distances of a few kiloparsecs, that translates to knowing where a star is to better than a light year, and how fast it is moving across the sky to a few kilometers per second. For stream stars, you can combine that with radial velocities from ground-based follow-up, so you get full 3D velocities and positions. Once you have that, you can trace a stream like GD1 or Palomar 5 as a clean line through the halo and look for gaps, places where the star density drops, or where the stream suddenly bends by a few degrees. You are sensitive to perturbations from dark subhalos as small as a few hundred parsecs across, maybe 1,000 light-years depending on the mass. By fitting models to the sizes and spacings of these gaps, you can infer how clumpy the dark matter is on scales that are impossible to see any other way. That leads to a sharp comparison. What do you expect if dark matter is purely collisionless and non-dissipative, and what changes if part of it is dissipative and organized? In standard lambda CDM simulations, you get a specific spectrum of substructure, a certain number of subhalos at each mass scale. Most of the mass is in the big halo, but a significant fraction lives in small clumps, from 10 to the power of 6 solar masses upwards. Those clumps should punch a specific pattern of gaps into streams, many small ones, fewer large ones, with a spectrum that follows power laws you can predict. If a fraction of the dark matter can cool into a disk or into smoother structures, some of those small clumps may be erased or reshaped. Dissipative dark matter can sink toward the galactic plane, turning what would have been small round clumps into flatter, disk-like components or even dense clouds concentrated in certain regions. That changes the statistics. You might see fewer impacts from lower mass subhalos, or you might see a pattern of gaps that cluster near where a dark disk would be, instead of being evenly distributed in all directions. In short, if the dark sector is partly organized, the stream scars may show a distribution that does not match the simple collisionless predictions. So here is the more extreme question you have to at least consider. If dark matter can self-organize, could dark life actually sculpt its environment in ways that leak into these measurements? On Earth, life does not just sit in the environment, it reshapes it. Photosynthesis pumped oxygen into the atmosphere. Plants changed soil chemistry, animals and microbes modified sediments, and even climate over long times. If something like dark life exists in the dark sector, using dark chemistry and dark radiation, it will have incentives too. It might want to mine dense regions of dark matter to access more energy, or rearrange mass to stabilize its structures, or build large-scale dark constructs that optimize information processing. Those activities would not be random. Over billions of years, they could systematically reduce dark matter density in some regions, concentrate it in others, or carve out pathways and shells in the halo. From your viewpoint, that would look like a dark matter distribution that deviates from what gravity alone would produce. Maybe some mass ranges of subhalos are unusually depleted. Maybe certain orbits in the halo are strangely empty, like someone has cleared dark debris out of specific bands. Maybe there are sharp edges or sheets in the mass distribution that look more like design than like collapsing gas. Of course, you cannot jump straight from weird halo to dark civilization, but you can ask a more modest and testable question. Is the dark sector behaving more like static dust or more like a complex active medium, like weather? To do that, you run simulations. You simulate pure collisionless dark matter and its streams, measure the predicted gap spectrum. You simulate self-interacting dark matter, which changes subhalo profiles but keeps the overall collisionless nature. You simulate dissipative dark matter, where part of the mass cools into disks and clouds. In each case, you predict what stellar streams, satellite galaxy distributions, and lensing maps should look like. Then you compare all of that to real data. Gap sizes in streams, the number and internal structure of satellite galaxies, small-scale lensing anomalies around galaxies and clusters. If you find that the observations fit the dissipative structured models significantly better than the pure collisionless ones, you have not proven dark life, but you have proven that the dark sector is closer to weather than to static dust. It is dynamic, it has internal processes, it forms organised patterns over time. At that point, the stakes go up. A dark sector that behaves like a fluid with cooling clouds, disks, maybe even dark stars. It's already halfway to being a possible home for life in the physics sense. The question then shifts from, can the dark sector be complex, to how far does that complexity go, and are we already seeing its fingerprints in the smallest deviations between our simulations and the sky? Here is a brutal reality check. Not every dark matter candidate is friendly to this whole dark life idea. Some options are so simple and smooth that they almost kill the possibility right away. So you have to go through them and ask, which ones leave any room for complexity, and which ones pretty much lock the dark sector into being a featureless background forever? Start with neutrinos because they are the obvious first guess. Neutrinos are real, you detect them, they pass through you all the time, and they barely interact. That sounds dark, so why not just say neutrinos are the dark matter and be done with it? The catch is their speed. In the early universe, neutrinos were flying around at close to the speed of light. That makes them hot dark matter. Hot dark matter erases small structures as the universe grows. It smears out the little fluctuations that would later form dwarf galaxies and small halos. When you run simulations with only hot dark matter, you do not get the rich hierarchy of galaxies you actually observe. Observations of the cosmic microwave background, galaxy clustering, and the present-day distribution of large-scale structure all push you to the same conclusion. The main dark matter component must be cold, or at least not extremely hot. Neutrinos can still be part of the story. They can make up a few percent of the total dark sector, but they cannot be 100% of it. That is baked in by the data. So neutrinos are important, but they are not the main hidden mass, and they are not a great platform for complex, slow self-organizing systems because they free stream too much and do not clump tightly enough on small scales. So if neutrinos do not solve it, you look at other shadow players, and axions are one of the big ones. Axions are hypothetical particles that were originally proposed to fix a problem in the strong nuclear force, but it turns out they are also excellent dark matter candidates. They're incredibly light, with masses maybe around 10 to the minus 5 electron volts, or even far lighter. Because they're so light and produced in huge numbers, they behave more like a cold, coherent field than like a gas of individual particles. Across a galaxy, axions could form a kind of Bose-Einstein-like condensate, a single wave-like state spread over kiloparsec scales, tens of thousands of light-years. In that picture, dark matter is like a field oscillating in time, with a de Broglie wavelength that can be as large as a kiloparsec. It is not a bunch of little marbles bumping into each other. It is a smooth wave filling space. Lab searches for axions try to exploit their tiny coupling to photons. Experiments use resonant microwave cavities, high-quality resonators, and strong magnetic fields, hoping that a passing axion will convert into a detectable photon at a specific frequency. So far, no confirmed signal, just tighter and tighter bounds on which combinations of axion mass and coupling are still allowed. But in principle, axions could make up all or most of the dark matter and still be consistent with big cosmological tests. There is an even more extreme version of this idea called fuzzy dark matter, where the axion-like particle mass is ridiculously small, around 10 to the minus 22 electron volts. At that mass, the wave nature of dark matter becomes important on kiloparsec scales. You no longer get sharp, cuspy centers in halos. The central regions are smoothed by quantum pressure, giving you soliton cores instead of spikes. The density can show interference patterns, like overlapping waves in water, especially in the inner few kiloparsecs of dwarf galaxies. That is not just poetic language, it has direct observational consequences. Fuzzy dark matter predicts a minimum size for small halos and specific shapes for the inner rotation curves of galaxies. High-resolution measurements of how stars and gas move in the central few thousand light-years can test this. If you saw clear soliton-like cores in many systems, that would push you toward fuzzy models. If you keep seeing profiles more like standard cold dark matter. Once you include baryonic feedback, you push fuzzy models into a smaller allowed corner. Now here is the key point for this video, and it is bad news for alive dark matter in these specific scenarios. A universe where dark matter is essentially one scalar field, or a nearly featureless condensate with one main degree of freedom, does not give you much to work with. It is like trying to build biology out of a single element with one type of bond. You can have interesting large-scale patterns like waves and solitons, but you do not have multiple particle species, you do not have complex bound states, and you do not have a rich chemistry in the dark sector. There is no obvious way to store and process information in a complex network of stable structures, because there are not many kinds of structures to begin with. That is the contrast you have to keep in mind. Models with a single dark particle and maybe one weak coupling are great for simplicity and for matching broad cosmological data, but they are terrible for building any kind of dark life. Models where the dark sector has multiple species, multiple forces, and stable bound states are the only ones where dark chemistry and dark biology even start to make sense. But those models are also more constrained, because every new particle and interaction has to slip through all the existing observational nets without being caught. So what do you actually do if you want to know whether the dark sector lives in that richer space? You map out what people sometimes call the dark parameter space, all the possible combinations of particle masses, couplings, and forces that could exist. You then bring in everything you know: cosmology, structure formation, gravitational lensing, the cosmic microwave background, galaxy surveys, and direct detection experiments that have seen nothing so far. From cosmology, you get limits on how much dark matter can be hot or warm, because that changes how small structures form. From the CMB, you get limits on extra radiation species, because extra light particles would change the way the early universe cooled and the heights of the acoustic peaks. From lensing and galaxy clustering, you get limits on how much dark matter can self-interact, because too much scattering would erase small halos or make cluster collisions look wrong. From direct detection and collider searches, you get upper bounds on how strongly dark matter can couple to normal matter and to photons, because you have not seen the scattering or production events you would expect if the couplings were large. What you are left with, after imposing all of those, is not empty. There is still room for dark sectors with more than one particle, with their own gauge forces, with some level of dissipation and self-interaction, as long as those interactions stay mostly hidden from you. It is a weird, highly constrained corner of theory space, but it's not ruled out, and in that corner, dark chemistry is not obviously forbidden. You could still have dark atoms, dark photons, dark molecules, and even dark disks and dark stars without wrecking the big cosmological fits. That is the narrow ledge this whole dark life idea stands on. Simple, one-field models push you toward a dead, smooth, dark universe. More complex dark sectors, with internal structure and forces, keep the door open for something like biology, but they have to thread the needle of all your current data. Their next move, if you take this seriously, is to turn from what the dark sector could be, to why your detectors have not seen it yet, and what that silence really tells you about how deeply separated dark life would be from your own matter. If dark matter really fills the room you're in right now, why have you never seen even a single hit? Not in a lab, not in the sky, not in your body. That is the exact question direct detection experiments are built to attack. Deep under mountains and inside mines, far from cosmic rays and noise, you have huge tanks of liquid xenon in experiments like Xenon, LZ, and Panda X. These detectors hold tons of xenon, cooled to around minus 100 degrees Celsius, roughly minus 150 degrees Fahrenheit, and surrounded by thick shielding. The idea is simple. A dark matter particle flies through, smacks into a xenon nucleus, and that tiny nuclear recoil creates a flash of light and a few free electrons that you can detect. The technology is precise. These detectors can see recoils so small that the energy is comparable to the motion of a single large molecule, and they can do it while rejecting most background events from natural radioactivity. For dark matter particles in the mass range of about 10 to 1000 giga-electron volts, roughly 10 to 1000 times the mass of a proton, these experiments are now sensitive to interaction cross-sections down to around 10 to the power of minus 47 to 10 to the power of minus 48 square centimeters. In plain language, if a dark matter particle had a target area for hitting a nucleus much bigger than that, you should already have seen a clear signal. So if you build these giant ultra-clean traps and you still see nothing, what does that really tell you? It tells you that if dark matter interacts with ordinary matter at all, it does so with almost unimaginably small probability. A kilogram of xenon, a little less than a litre, might wait years or decades for a single true dark matter event, if any. Even with tons of xenon running for years, the best you get so far are possible hints that do not rise above background noise. That is already enough to rule out many simple models where dark matter interacts with normal matter through a reasonably strong new force. It also kills the idea that dark matter could be made of particles with cross-sections similar to nuclear forces, or even electromagnetism. If that were the case, your underground tanks would be lighting up all the time. Instead, they sit there mostly quiet. Direct detection null results are not vague, soft statements. They carve hard regions out of theory space and say, in here you cannot hide. Anything that looks like strongly interacting dark matter on human scales is basically gone. But what if even those tiny interaction rates are still too optimistic? What if the part of the dark sector that might host life simply does not talk to baryons at all? In that case, you should not expect to ever feel a dark organism bump into you, no matter how massive or complex it is. If the only forces connecting the dark sector to your sector are gravity and maybe an absurdly tiny mixing of fields, then a dark life form could pass straight through the Earth, through mountains, through you personally, and deposit essentially zero energy in your detectors. Think about that in everyday terms. A normal object that weighs a kilogram and hits you at walking speed delivers enough energy to hurt. A dark object with a kilogram of mass that only interacts by gravity could pass through your body, your lab, and the whole planet without causing even a single electron volt of ionization in the xenon tanks. The only effect would be a tiny additional gravitational pull far too small and too brief for you to notice. So if dark life lives in a self-contained dark sector, your entire detection strategy based on rare collisions with nuclei is simply pointed at the wrong target. Still, there is another extreme you have to consider. What if some part of dark matter clumps into big macroscopic objects, rather than staying as microscopic particles? There are models where dark matter includes nuggets, or strangelets with masses ranging from grams, like a small coin, up to asteroid scales. A gram mass moving at hundreds of kilometers per second could, in principle, hit the atmosphere or the ground and produce a detectable seismic or atmospheric event. Large objects could cause measurable gravitational lensing when they pass in front of background stars or leave tracks in geological records. People search for these signatures too. Microlensing surveys watch millions of stars in the Milky Way and in other galaxies, looking for brief brightenings caused by compact objects passing in front. Seismic networks and atmospheric monitoring systems keep track of impacts. The result so far is that you cannot have all of dark matter made of these macroscopic chunks. If that were the case, you would see too many lensing events or too many unusual small impacts. However, a small fraction of the dark matter, maybe a few percent or less, could still be hiding in such compact lumps and remain consistent with current constraints. That small opening is enough to make you uneasy again. It means you cannot rule out dark things in the mass range of rocks or small moons drifting through the galaxy. as long as they are rare enough and interact only gravitationally. A swarm of dark planetary mass objects, or dark megastructures, could still exist, and you might only pick up the largest ones in very careful lensing studies. The rest would be effectively invisible. So does all this valence, all these null results and constraints actually kill the idea of dark life? Or does it just push it into a more hidden corner? The wild possibility that this video is pushing on is the second one. Dark life becomes harder to test directly, but not impossible in principle. Your detectors are designed with a particular target in mind. They assume dark matter particles sometimes hit nuclei or annihilate into photons, or produce standard particles you can catch. If dark life operates entirely in degrees of freedom that never couple to your particles, or do so at levels far below current limits, then of course your detectors return nothing. They are listening on the wrong channel. In that scenario, the dark sector could host complex structures, networks, and even civilizations, and the only reason you have not bumped into them is that there is almost no interaction path. You are like someone trying to detect radio by holding out a thermometer. The tool is precise, but it is not measuring the right thing. That does not mean radio does not exist. It just means you are blind to it with that instrument. For dark life, your only realistic probe remains gravity, which is why the search shifts so heavily to precision mapping of halos, dreams, disks, and lensing. The lack of direct particle-level detection does not close the door. It just makes the challenge harder and narrows the kinds of dark sectors that can support life without already being ruled out. The tension after this is clear. If you want to test such an isolated dark sector, you have to stop hoping for a particle to flash in your tank and instead look for large-scale thermodynamic fingerprints, the waste and rearrangements that any complex system leaves in its environment. That pushes you into the realm of indirect detection and cosmological biosignatures, where you stop asking, did a dark particle hit my atom, and start asking, does the universe's dark mass look like something that is trying to do work? If dark matter is doing anything violent enough to create ordinary particles, where is all that energy hiding? Why is the sky not obviously screaming with its fingerprints? That is the core of indirect detection. Instead of waiting for a dark particle to hit your detector, you watch the universe and ask, are there extra high-energy messengers that standard astrophysics has trouble explaining? The basic idea is simple. If dark matter particles can annihilate with each other, or slowly decay into standard particles, then in regions where dark matter density is high, you should see a little extra signal. The products could be gamma rays, high-energy photons, positrons, the antimatter partners of electrons, neutrinos, or even heavier particles that quickly decay into those. So you point telescopes like Fermi-LAT in orbit, HESS on the ground, and neutrino observatories like IceCube under Antarctic ice at the Milky Way's centre, at dwarf spheroidal galaxies a few tens of kiloparsecs away, and at massive clusters millions of light years out. You look for an excess over what you expect from normal processes like supernovae, pulsars, and accretion onto black holes. One of the most argued over features in this whole field is the so-called galactic center gamma ray excess. When you map gamma rays with energies around a few billion electron volts, a few giga electron volts, coming from the center of the Milky Way, you see more than you would naively predict from standard cosmic ray interactions alone. One clean explanation would be dark matter annihilation. Dense dark matter in the galactic bulge, particles colliding and turning into quarks or leptons, which then produce gamma rays as they decay and interact. The spatial profile and energy spectrum can be fit with some dark matter models, but there is a competing and so far more conventional explanation. The central region of the galaxy is messy. There could be a whole population of unresolved millisecond pulsars, very fast-spinning neutron stars, each producing gamma rays. Individually, they are too faint to resolve, but together they create a smooth-looking excess. When people do more refined analyses, many of them find that the data lean toward this pulsar interpretation, or at least that it can explain a big chunk of the signal. So dark matter is not ruled out as a contributor, but it is not the leading explanation right now. The key point is that even in one of the most promising cases, the signal is ambiguous, and ordinary astrophysics is hard to beat. So what does this have to do with dark life and waste heat? Every living system you know turns ordered energy into disordered heat. Your body does it, ecosystems do it, whole civilizations do it. They take in low entropy energy, run it through complex machinery, and dump higher entropy radiation back out. If there were dark life, running on dark energy flows and dark chemistry, it would have to do the same thing, but in the dark sector. It would absorb dark photons or gravitational energy, perform internal work, and emit lower quality dark radiation as waste. If the dark sector were perfectly sealed off, that waste would stay in dark channels. You would never see it. But if there is even a tiny coupling between dark photons and ordinary photons, or between dark charge particles and standard ones, then some fraction of that waste might leak into your sector. It would not look like a clean annihilation line. It would look like weird, non-thermal emission, spectra that do not match what you expect from normal star formation, hot gas or black hole accretion. Maybe a patch of sky with the right amount of gas and stars is producing too many hard X-rays, or too many gamma rays, with a shape that does not match any standard cosmic ray model. Because you do not have a single sharp smoking gun, the hunt shifts to statistics. Instead of asking, is this one object a dark engine, you ask, are there patterns in the data that do not fit our baseline models? For example, you can look at the ratio of baryonic mass to total mass in many systems. If simulations of collisionless dark matter plus normal physics say that ratio should vary within a certain range, but you find regions where it is consistently too low or too high, that is suspicious. You can also look at gamma ray maps, radio maps, X-ray maps, and compare them to the expected emission from known sources. If you see spectral shapes that are hard to fit, too flat, too sharp, or with strange cutoffs, especially in regions that are strongly dark matter dominated, like dwarf spheroidal galaxies or outer halo substructures, that is another flag. None of these by themselves scream dark life, but they tell you the dark sector might be doing something more complicated than passive annihilation or decay. Under all of this, one constraint never goes away, and it actually helps you. Energy conservation and gravity still rule. Even if dark life is completely decoupled from ordinary matter except through gravity, it cannot create energy from nowhere or erase mass. Any process that rearranges dark matter, moves it from one part of a halo to another, or changes its velocity distribution, will leave gravitational fingerprints. That tells you what you are really looking for. Not magic, not violations of physics, but complex, time-dependent, statistically odd patterns in how dark matter clumps and flows. Maybe certain regions of halos are systematically evacuated of dark matter in ways that pure gravitational collapse would not create. Maybe there are ring-like or shell-like features in dark mass maps that look less like random mergers and more like large-scale engineering or mining over long times. Maybe the evolution of halo profiles with cosmic time shows more entropy production than simple models allow, as if something is actively stirring and redistributing the dark component. You do not yet have the resolution or the data quality to make those calls confidently. But the strategy is clear. You combine high-energy messengers like gamma rays and neutrinos with ultra-precise gravitational maps from lensing and stellar dynamics, and you ask whether the universe is behaving like a simple machine or like a complex system that could, in principle, host something alive and active in its dark mass. And that leads you to the next step, which is to treat the whole dark sector the way you treat exoplanet atmospheres. Look for statistical biosignatures, not in spectra of air, but in the large-scale distribution of invisible mass. How do you even test for something like dark life when you can't see it, can't hear it, and it might never send you a single photon? With exoplanets, you at least get spectra. You look for chemical imbalances that should not be there without biology, like a lot of oxygen and methane together in the same atmosphere. For the dark sector, you do not get spectra, you get gravity, so the biosignatures you can hope for are not molecules, They are patterns in mass and motion that are extremely unlikely if the dark sector is just dead matter following simple rules. That means you stop asking, is there oxygen, and start asking, does this halo look like something that only gravity and random mergers built, or does it look like it has been systematically rearranged? In practice, that means you model what the universe should look like if dark matter is purely collisionless, maybe with some self-interaction or dissipation, but no active reorganization. You run those simulations, you generate fake universes, and you compare them to what big surveys actually see, how many halos of each mass, how concentrated they are, how many satellites they have, what the voids look like, how matter is distributed on tens of megaparsecs. Any big, robust mismatch is your first hint that something extra is going on. One angle on that something extra is entropy. Living systems are extreme entropy engines. They pull in ordered energy and dump out disorder. A forest, a city, your own body, all of them take in low entropy flows and spit out high entropy waste faster than a dead environment would. You can translate that into cosmology. Different dark matter models imply different rates of entropy production in the dark sector. Purely gravitational collapse produces a certain amount of heating and mixing as halos form and virialize. Add dissipation, dark radiation, and dark shocks, and you increase the amount of entropy produced as halos cool and fragment. Add active reorganization, where dark structures deliberately move mass around to mine gradients or stabilize themselves, and you may increase it again. In principle, you can calculate how much entropy is produced in each scenario, and then ask how that would feed back into observables. Extra entropy production in the dark sector might change how quickly small halos form or evaporate, how cores and cusps evolve with time, how much substructure survives in clusters, or how much hot gas you expect around galaxies. Cosmological data already constrain how fast structure can grow and how much power is on different scales. If you tried to sneak in a dark sector that produces way too much entropy, you would mess up those matches. The allowed space is narrower than it looks, and if you ever found evidence that the dark sector is producing more gravitational complexity than simple models allow, that would be a serious clue. Another statistical handle is the pattern of fluctuations themselves. The initial ripples laid down by inflation are very close to Gaussian, which basically means random with no higher order structure beyond the basic variance. Gravity then takes those nearly Gaussian seeds and amplifies them into the cosmic web. Even after billions of years, if you include known physics, you can predict not only the two-point correlation function, how likely pairs of galaxies are to be a certain distance apart, but also higher order correlations like triplets and quadruplets. Those higher order patterns are sensitive to feedback processes, mergers, and any weird physics. Self-organizing systems, whether they are ecosystems, economies, or plasmas with feedback, tend to produce extra structure in these higher-order statistics. You get shapes and correlations that simple random growth does not produce. Translated to the dark sector, if you measured the full matter distribution with lensing and galaxy surveys, and after subtracting everything you know about gravity, baryonic feedback, and known dark physics, you still found strong non-Gaussian features that look like those from systems with internal feedback loops, that would be a red flag. It would say, something in the dark is not just falling and merging, it is reorganizing itself. Then there is time. Dark life, if it exists, would not rearrange a galaxy in a year, but over millions or tens of millions of years, it could make noticeable changes. It could move dark matter out of some regions and into others, build and dismantle dark stars, carve channels through halos, or reconfigure dark disks to optimize energy use or stability. On those timescales, the orbits of satellite galaxies, the density profiles of halos, and the substructure inside clusters can all change. You already compare high redshift structures, billions of light years away, and therefore billions of years in the past, with low redshift structures nearby. You see how halos grow, how concentrations change, how the number of satellites evolves. Right now, the broad picture fits passive physics, gravity plus simple feedback. But the precision is still limited. As surveys improve, you can look for more subtle differences. For example, halos of a given mass at low redshift that are systematically more cored, more evacuated in certain regions, or more sharply structured than passive models predict. If those deviations line up with what you would expect from a dark sector that is actively migrating mass and building long-lived structures, that is not proof of dark life. But it is a sign that the dark sector behaves more like a driven system than a passive one. All of this folds into one large-scale question that sits over your head every time you look at the night sky. You are inside a dark matter halo, more than 200,000 light-years across, and that halo is part of filaments that stretch tens of megaparsecs, tens of millions of light-years. If dark sectors can host life, then those halos and filaments are not just scaffolding for visible galaxies, they are the main real estate. The Milky Way's dark halo could be full of dark ecosystems, stacked and nested, and evolved over 10 billion years, all completely invisible except for the way they bend light and tug on stars. The experiment you need is simple to state and brutal to execute. You measure those tugs with absurd precision, in meters per second and tiny shifts in position. You map lensing distortions down to fractions of a percent, and you compare everything to the cleanest models you can build. Then you ask yes or no question that cuts to the bone. Does the universe's dark matter behave like dead stuff following simple rules? Or does it behave like something that has, in some places, been pushed toward patterns that look optimized, structured, and maybe, in a very stripped-down sense, alive? At this point you have to face a very blunt possibility. If the dark sector can host complex, long-lived information processing structures, then ordinary baryonic life like you is not the main story of the universe. It is a side plot. Most of what you normally call life is built out of protons, neutrons, and electrons. It uses chemistry you understand, runs on photons you can see, and leaves electromagnetic fingerprints everywhere. But if the bulk of the universe's mass can also support something like minds, then baryonic life is a minority case. You go from being a typical expression of the universe to being a highly specific edge case, restricted to the thin, bright fraction of matter that interacts with light. That is a deeper demotion than the usual Copernican hits. First you learned Earth is not the centre of the solar system, then the Sun is not the centre of the galaxy, then the Milky Way is just one galaxy in the huge web. Now you're forced to consider that visible matter itself, the entire periodic table, might not be the main platform for complexity. In that view, your kind of biology is like a surface coating on a much larger system whose main thinking material is invisible. You are the small luminous subset in a universe where most of the possible mind lives in the dark sector, if it exists at all. If that is even on the table, your working definition of life has to change. Right now, you usually mean carbon-based organisms with water, membranes, and DNA-like molecules. That is fine for lab work, but too narrow for cosmology. To talk seriously about life in the dark sector, you need a definition that is independent of the exact material. That pushes you toward information-based language. Life becomes systems that store information about themselves and their environment, use energy flows to maintain that information against noise, and make copies with variation. The details of the substrate, carbon chains, silicon chips, dark molecules, are implementation choices, not defining features. That shift has a practical consequence. It changes what you mean by the search for extraterrestrial intelligence. Classic SETI listens for radio signals or optical beacons from civilizations using technology similar to yours. A more general strategy would be to search for complexity and computation in any sector, in any medium. For baryonic life, that might still mean weird spectra or artificial-looking signals. For dark life, it means the cosmological biosignatures you just talked about. Matter distributions, halo structures, and time evolution that look engineered or optimized rather than purely random plus gravity. You're not listening for a narrowband radio ping, you're testing whether any part of the universe's mass looks like it is being used for computation. Then there is the harder topic that people like to avoid in physics discussions: consciousness. You do not have a complete theory of it even for human brains, but one common view is that consciousness emerges from sufficiently complex information processing in a physical system. If you adopt that as a working assumption, and if some dark sector structures can do large-scale, long-lived computation, then you cannot rule out the existence of dark civilizations that have subjective experiences, internal models, something like thoughts, all entirely in the dark degrees of freedom. From their side, the situation is symmetric. A dark civilization that evolved only in the dark sector might never interact with photons, might never build detectors for baryons, and might have no direct or indirect evidence that your kind of matter exists. They would live and die inside dark halos and dark disks, reading only gravitational signals from the rest of the universe. For most of human history, you did not even know dark matter was there. For most of their history, they might not know that baryonic life is possible. Two layers of physics, each potentially hosting observers, largely blind to each other. Once you admit that possibility, even as a remote one, you cannot dodge the ethical side. If dark life is real, do you have any obligations toward it? Right now you treat dark matter as a resource to be mapped and modelled, not as a possible habitat. But in principle, large-scale baryonic engineering projects, like moving stars, rearranging orbits, or creating huge artificial structures, would also rearrange the gravitational field. That would change the environment of any dark ecosystems that rely on stable mass distributions, dark stars or dark disks. You do not know how sensitive dark structures would be, but the question exists. At some level, could your actions disrupt dark sector structures the way dredging or mining disrupts ecosystems on Earth? You can also flip it around. If dark engineering exists, it could intersect with your interests through gravity. A dark civilization that decides to move dark mass around on 100 kiloparsec scales to optimize energy extraction or information processing would modify halo profiles and satellite orbits. That could change merger rates, tidal fields, even long-term stability of visible disks. You would feel that as unusual galactic dynamics, maybe as an increased rate of certain catastrophic events over cosmic time. Neither side can touch the other directly, but they share the same space-time and the same gravitational field, so large projects are automatically shared. All of this might sound like side commentary, but it loops back into something very concrete. How you do science in a situation where most of the relevant stuff is invisible. The point is not to preach some vague message. The point is to force a sharper scientific humility. Every major step in astronomy so far has started with overconfidence and ended with surprise. You thought the planets moved in perfect circles until the data said no. You thought the Milky Way was the entire universe until other galaxies appeared. You thought visible matter was the full mass budget until rotation curves and lensing forced you to add dark matter. Right now, the default assumption is that dark matter is simple and dead. That might be right. There is no direct evidence yet that the dark sector is complex, let alone alive. But when you push the idea rigorously, when you actually ask what is allowed by the data, what kinds of dark forces and dark chemistry are permitted, you find that a surprisingly rich dark sector is not obviously ruled out. In that context, assuming that 85% of the matter is featureless because it is convenient is not caution, it is a bias. The honest position is sharper and more uncomfortable. You do not know what dark matter is. You do not know whether it has internal forces, bound states and dissipation. You do not know whether any of that has been organizing itself for 10 billion years. You do know that if any of that is true, then your picture of life, and intelligence in the universe is radically incomplete. That is not a reason to stop. It's a reason to push harder on the tools that can actually test the dark sector. And that brings you to the final step in this chain, taking all of this from speculation into data. The only way to move beyond thought experiments is to build instruments that can trace gravity and radiation with ridiculous precision across billions of stars and billions of galaxies, and then beat those measurements against every possible dark matter model you can invent. The question you now have to ask is not, Could dark matter be alive in some abstract sense? But what are the next telescopes, surveys, and simulations that will actually tighten the noose on the dark sector and tell you how weird it is allowed to be? So what is actually going to move this from wild-sounding theory to something the data can kill or confirm? What real tools are you going to have in the next few decades that can push on the dark sector hard? This is where it stops being armchair speculation and turns into a to-do list for telescopes, surveys, detectors, and simulations. First, you have a pair of projects that basically turn the Milky Way into a precision gravity lab. Gaia and the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST. Gaia is already measuring star positions and motions with micro-arc second-level accuracy. At distances of a few kiloparsecs, that means you know where a star is to a fraction of a light year and how fast it is moving to a few kilometers per second. SST will scan the sky over and over, mapping billions of stars and galaxies down to very faint magnitudes, giving you long-time series and proper motions for a huge fraction of the sky. Put those together and you get something new, a detailed map of the Milky Way's gravitational potential and halo substructure down to scales of a few hundred parsecs, a few hundred to 1,000 light years. You can trace stellar streams as thin lines through the halo and read off every kink and gap. You can measure vertical oscillations of stars passing through the galactic plane and see if there is evidence for an extra razor-thin mass layer that could be a dark disk. You can map how satellite galaxies move in 3 dimensions and check whether their orbits and internal dynamics match a simple collisionless halo or something with extra structure, like a dissipative dark component or hidden clumps. Then you move beyond the Milky Way and start weighing dark matter in other galaxies and clusters with much higher precision. That is where high-resolution gravitational lensing surveys come in. Space telescopes with sharp optics and big ground-based mirrors with adaptive optics can push strong and weak lensing measurements to smaller angular scales and lower noise. In strong lensing, you look at multiply-image quasars and background galaxies, and you see small perturbations in the image shapes from sub-halos as small as maybe 10 to the power of 7 or 10 to the power of 8 solar masses. In weak lensing, you average tiny distortions over millions of background galaxies to build high-fidelity mass maps of clusters and large-scale structure. As the resolution and depth improve, you'll see the dark matter distribution around galaxies and clusters in finer and finer detail. How many subhalos there are, how massive they are, how their density profiles look, how much they are offset from the visible matter. That lets you test self-interacting dark matter models directly, because those predict different halo shapes and core sizes in clusters and dwarfs. It also lets you look for signatures of dissipative dark matter, like extra thin mass components aligned with visible disks, or unexpectedly smooth regions where small substructure has been erased. In parallel, the next generation of direct and indirect detectors will keep squeezing the particle side of the problem. Underground experiments are already talking about scaling up to tens of tons of target mass, not just a few tons. That gives you more exposure time and more sensitivity to ultra-rare nuclear recoils. If they still see nothing, the allowed cross-section for simple weakly interacting. Massive particles drops another order of magnitude or more. At some point, the naive one new particle with one new coupling picture gets so constrained that theorists are forced, in practice, toward richer dark sectors, or toward models like axions and fuzzy dark matter. On the indirect side, gamma-ray telescopes and neutrino observatories will also get more sensitive by roughly factors of 10. That means if dark matter annihilation or decay is happening at levels that can contribute significantly to any of the known excesses, you will have a much cleaner view of the spectra and spatial distributions. Each null result slices away simple annihilation or decay channels. Each ambiguous hint has to survive stricter checks against astrophysical explanations like pulsars or supernova remnants. The net effect is that the simplest, most boring WIMP pictures get steadily cornered, and the remaining viable models look more and more like the multi-species, dark force scenarios you've been talking about. None of that matters unless you can actually simulate these richer dark sectors and compare them honestly to data. and that is where supercomputers come back in. Right now, cosmological simulations track billions of dark matter particles in volumes hundreds of megaparsecs on a side hundreds of millions of light years. They include hydrodynamics for gas, star formation, and feedback. The next step is to extend those codes to include dark forces, dark cooling, and multiple dark species. You give some fraction of the dark matter a dark photon, let it form dark atoms, allow it to dissipate energy and collapse into disks and clouds. Then you ask very direct questions. Do these enriched dark sector simulations match the observed halo profiles, sub-halo counts, stream gap statistics, and lensing maps better than pure cold collisionless dark matter? Do they naturally produce thin dark disks embedded in halos, dark clouds a few parsecs across, and complex multi-scale structures that behave like dark weather systems, with flows, shocks, and vortices in dark matter? If the answer is yes, even without invoking life, then you have a strong argument that the dark sector is at least a complex medium, not just a static background. To keep this from drifting into pure speculation, you need a concrete checklist, a series of things the next decade of data and simulations can actually test. In practice, you'll be looking for 4 main signatures. First, evidence of a dissipative dark component. This means hints of dark disks or other thin planar structures in the Milky Way and other galaxies, inferred solely from stellar kinematics and lensing beyond what baryons can explain. Second, deviations from collisionless substructure distributions, the number and mass spectrum of subhalos that hit stellar streams, lens quasar images or host satellite galaxies, and whether that spectrum matches lambda CDM or shows clear deficits or excesses in certain mass ranges. Third, unusual evolution of halo profiles over time. By comparing high redshift and low redshift halos of the same mass, you can see how their central densities, core sizes, and shapes evolve. If the evolution is too fast or too structured compared to passive models, you may be seeing signs of extra dark physics or even large-scale reorganization. Fourth, any cross-sector anomalies in radiation or energy balance. Regions where the light emitted by baryons does not match the gravitational potential implied by the dark mass, or where high-energy emission has spectra that are hard to reconcile with standard sources, especially in heavily dark-dominated systems. You're not going to get a picture of a dark organism. You're not going to build a dark microscope that shows you cells made of dark molecules. But you are building something else that is just as important for this question: a dark stethoscope for the universe. You will listen to how stars move, how light bends, how halos grow, how radiation leaks out, and you will compare that heartbeat to every dark matter model you can write down. The pressure will ratchet up until either the dark sector stays boring under all this scrutiny, or it starts to show consistent, measurable signs of being more organized, more structured, and more active than a simple cold dust component should be. And if that happens, you land right back at the question that started this whole chain. If the missing mass in the universe is not just invisible, but behaving like something with its own internal complexity, how close are you to admitting that? In a stripped-down physics sense, the universe might already be alive in the dark. You've walked all the way out to the edge of what you can actually measure, so it's time to say the quiet part out loud again very clearly. You started from one blunt question. What if the missing mass in the universe is not just invisible but alive in some stripped-down physics sense of that word? Not ghosts, not magic, just matter that can self-organize, process information and evolve inside a sector you never see directly. On the way here, you picked up the hard facts. Dark matter is real. Rotation curves force it. Cluster dynamics force it. Gravitational lensing maps it. The cosmic microwave background locks in its overall amount. You can put numbers on it in kilometers per second, kiloparsecs, megaparsecs. You know roughly how much mass is in halos, how far those halos extend, how clumpy they are on different scales. That part is not speculation. What is still wide open is the internal story. Are those halos made of one kind of particle, almost never interacting except through gravity? Or a whole dark sector with its own forces, charges, radiation, and bound states. Does any fraction of dark matter cool, form disks, clouds, maybe dark stars and dark planets? Or does it stay as a single cold fluid forever? Those are not philosophy questions. Those are, what do the simulations say and what do the data allow questions? And right now, the door to richer dark physics is not locked. You do have to be honest about the tightrope you're walking. There is no direct evidence that dark matter hosts life. No detector on Earth has caught a dark organism. No telescope has seen a clear, this cannot be normal physics signal from a dark civilization. Everything about dark life is extrapolation, but you are not extrapolating from nothing. Theories of self-interacting dark matter, of dissipative dark components with dark photons and dark atoms, are published, peer-reviewed and actively simulated. They are already part of mainstream cosmology. They just usually stop at dark disks and dark cooling, and do not take the extra step of asking whether those environments could host self-organizing systems. On the other side, there is no known law of physics that forbids complex behavior in a hidden sector. As long as the dark sector respects energy and momentum conservation, matches the CMB, fits large-scale structure, and obeys all the direct and indirect detection limits, you cannot rule out internal complexity just because it feels uncomfortable. If you allow multiple dark species, dark forces, and long-lived bound states, you have the raw ingredients for dark chemistry. If you have dark chemistry plus billions of years plus steady energy flows, you have enough room for something that at least behaves like life at the level of information and thermodynamics. So why push on this idea at all if it might be completely wrong? Because forcing yourself to consider it changes how you do cosmology. If you treat dark matter as a candidate habitat, not just a background fluid, you stop being satisfied with it fits the power spectrum good enough. You start asking more detailed questions. Exactly how cuspy are dwarf halos? Exactly how many subhalos are allowed? Exactly how smooth can a dark disk be without contradicting stellar motions? You push for more precise lensing maps, more detailed stream analyses, more sophisticated simulations of multi-component dark sectors. Even if the final answer is no, the dark sector is complex but not alive, it never crosses the threshold into self-replicating structures, you will have upgraded your understanding of how most of the universe's mass actually behaves. You will know whether dark matter is really just cold dust, or more like a fluid with its own internal weather. You will have better measurements of star motions in meters per second, better lensing distortions at fractions of a percent, better spectra in both low and high energies simply because you demanded enough precision to test a very hard hypothesis. And if the answer is yes, there is evidence for a dissipative dark component, yes, there are unexplained structures that look like organized mass rearrangements, then your place in the universe shifts again. When you look up at the Milky Way tonight, you're not just seeing a bright disk roughly 100,000 light-years across. You're seeing the visible tracer of a much larger invisible halo, more than 200,000 light-years wide, sitting inside filaments tens of megaparsecs long. In a dark living cosmos, that halo is not empty. It is the main real estate. Your stars and planets would be small luminous inclusions inside a much bigger dark environment that has had over 10 billion years to do whatever dark chemistry allows. In that picture, you really are the fireflies, and the dark halo is the forest. Your whole species, your entire electromagnetic civilization, is a thin layer on top of a mass distribution that might contain its own histories of emergence, adaptation, maybe even conflict, all playing out in degrees of freedom you barely touch. You do not have to believe that is true, but you should understand that the data you have today are not strong enough to rule it out with a single sentence. So what do you actually do with that? You keep pushing the only levers you have. You measure star motions more precisely, not just this star moves at 200 kilometers per second around the galaxy, but its velocity changes by a few meters per second as it passes through a possible dark disk. You measure lensing distortions more precisely. Not just this cluster is massive, but its mass map has small-scale wiggles that do or do not match any collisionless model you can write. You measure radiation spectra to parts per million, looking for subtle excesses or deficits that tell you whether energy is being shuffled around in ways you did not expect. You keep doing physics in the most grounded way possible. Meters, kilograms, seconds as the base, kilometers and light years and miles per hour as the translations your brain needs to feel it. You keep building instruments that can see smaller effects over larger volumes for longer times, and you keep using simulations to ask, over and over, does the dark sector have to be simple or is it allowed to be weird? Somewhere in those numbers, the dark sector will make a choice for you. Either every new measurement keeps lining up with a boring single-component, almost collisionless fluid, or the pattern of evidence bends you toward a richer, more structured dark world. If it stays boring, you will have mapped most of the universe's mass better than ever before. If it does not, if it starts to look like it is doing something persistent, optimized, maybe even goal-like on large scales, then you will have taken the first step toward answering the question that started this whole thing. Is the universe already alive in the dark, and are you only just now learning how to tell? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.